Welcome to the DDPS seminar, everyone. Before we introduce our invited speaker, let's go over some rules and logistics. First, please mute yourself during the talk, but if you have questions, you can unmute and ask questions, or use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audience. Therefore, no classified discussion is allowed, so please watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now, let me briefly introduce our speaker today. It is an honor to host Dr. Marius Zeinhofer, who received his Ph.D. from the University of Freiburg, Germany, where he researched multiphysics models for bone growth under the supervision of Professor Patrick Dondl. He then served as a postdoctoral research fellow at Simula Research Laboratory in Oslo, Norway, focusing on scientific machine learning with Professor Kent Andra Mardal. Currently, he is a researcher at the University Hospital Freiburg, specializing in AI for healthcare. His ongoing research interests include error analysis and optimization of neural network-based methods for solving partial differential equations. Today, Marius will talk about infinite dimensional optimization for scientific machine learning. I'm sure we are going to hear a wonderful talk. Before I pass the baton to Marius as a tradition to the DDPS seminar, let me ask a somewhat informal question so that we can we know something about Marius, somewhat out of the technical reason. So I happen to know you are very keen to guitar playing. If you can share your favorite piece, favorite music you would like to play.
Well, that's a difficult question. It changes.
Oh, is it?
Yes.
Okay.
Well, let's just go with the classics, which is Stairway to Heaven by Led Zeppelin.
Okay. As a non-guitar player, I never heard of that. But
Oh,
I'm
you
sure
can
it's pretty good.
it's a good one. You can check it out.
Okay, I will definitely check it out. Well,
Yeah.
thank you, Marius. The stage is yours.
Thank you. Thank you for the nice introduction. And let's get started. So today I'll talk about optimization for scientific machine learning. And talk will be structured in roughly two parts. First, and that's the specialty sort of our approach, is the function space perspective on the optimization for SciML problems. And what I will propose to you is for these kind of problems to adopt an infinite dimensional viewpoint or a continuous viewpoint, leaving out the ansatz class, and then develop optimizers or choose optimizers based on the infinite the properties on the function space level, and then discretize in a certain way that guarantees you that you mimic the function space dynamic. And with this principle in mind, we'll see how we can design new algorithms and also understand existing ones from that perspective. And then in the next step, after designing these optimization methods, we'll have a look into how you can scale them to large-scale neural networks. We'll do that with one specific strategy where we use the Kronecker structure of the linear layer Jacobians in the neural networks. The talk is mainly based on these two papers I've linked here below. One position paper, this year's SciML, and then a recent one, which is related to the second part, which is about the Kronecker-factored approximation. So let's dive in. Let's start with the function space optimization, and let's clarify sort of what kind of problems I want to talk about. I said scientific machine learning, and for me, or at least for this talk, mainly what I have in mind is operator learning, but also methods for Schrödinger's equation, the electron Schrödinger's equation with a neural network ansatz. Can be physics-informed neural networks formulations of partial differential equations or inverse problems. Could be deep RIDs, so rational formulations. Essentially anything that involves PDE terms in the loss function and neural networks. The methods will be well suited for all of them. And one observation, so the starting point also for our work in this direction is that as soon as you introduce PDEs to objective functions, the neural network training gets more difficult. Let me give you an illustration of that statement that optimization in SciML can be quite hard. I have two pictures here for you. The details are not so important. Let's look at the first one here. I've taken this from a recent paper, the forward Laplacian paper. So in this paper, they solved the many electron Schrödinger equation. What I want to stress here is the sheer amount of GPU hours that I used for a single solve. It is in the thousands, almost towards 10,000 GPU hours for a single problem. And then the other paper is a very simple problem. It's just a two-dimensional Poisson equation. And with a smooth solution, you formulated use the pin formulation and you optimize. Green is just full wedge gradient descent, and red is atom. And you see a huge amount of iterations and you see stagnating errors. So what we are going to do here is to abandon first order optimization and look into the structure on the infinite dimensional spaces. We want to exploit the geometry that is induced by the PDE operators to design smarter algorithms. And I have an informal roadmap here for you, how to do that. I call it first optimize, then discretize. So we're given a SciML problem and later also neural network ansatz. And the first thing we need to do is think about the continuous formulation. So we need to formulate a minimization problem. Let's say it's a minimization problem. It could be saddle points, root finding, whatever. So it's a minimization problem in a Hilbert space H. Well, that's a function space here. So E, the energy, that's what we want to minimize. So we need clarity about how that should look like. And then after we formulated our problem, we'll have a look in what are the properties of E, right? And here it's left abstract, there is no properties assumed, but in a practical application, it will have properties. And based on these properties on function space, we'll decide for an appropriate algorithm, set an appropriate iterative algorithm in function space. What I mean by that is you update your current iterate by a direction and you step until you're happy with it, right? But remember, this is in function space. This is nothing you can practically do. And to get something back which you can do in practice, which you can do on your machine, then you need to discretize. But note this is the last step. And discretization here, what I propose is to project the update direction, this would be dk, on the tangent space of your neural network ansatz, or on whatever your ansatz is. If it's not neural networks, it's also fine. So let us put that, make that concrete with a very, very simple example. The example is as simple as it can possibly be, arguably. So suppose we want to solve Poisson's equation on some domain omega. We have some forcing data. We have some boundary conditions. That's the starting point. Then I reformulate the equation, in this case, as a minimization problem. I've chosen here the simplest one. This would be physics-informed neural networks formulation. But of course, you could choose a variational formulation, or you could formulate it as a root-finding problem. But let's stick with this. So I've chosen here the Hilbert space is H2. This is how it looks. No ansatz class, no nothing, just a pure formulation. And then the next step is where we decide what optimization algorithm is appropriate for this kind of energy. So let's have a look. The PDE is linear, and we use L2 squared around the residual. So that makes this energy quadratic. So it's a quadratic function on function space. And as we all know, Newton's method for minimization builds at where you're at your current iterate, it builds a quadratic model of your objective function, and it minimizes that quadratic model. So Newton's method in function space for this energy has one-step convergence, no matter where you start. And if I write out Newton's method in function space, this is the way it looks like. Here's the Frechet derivative of our function space guy. This lives in the dual space. Here is the Hessian. This is a bilinear form, or alternatively, it maps from the primal to the dual space. This is the same thing essentially, and that's how it looks like. And if your energy looks different, you would probably choose something else than Newton. We'll see an example soon. And still no ansatz class. This is coming now. Now it's time to discretize. Now it's time when you choose your ansatz. And I left the ansatz generic. These, you could think of them as neural networks, but you could also think of them as finite element functions. Both is covered by the theory. Then the tangent space is given by the partial derivatives with respect to the parameters of our ansatz class. And the object that we're actually minimizing, which is no longer posed in function space, but posed in parameter space, this L is the loss function, and it's just pulling back our function space energy or parameter space, capital theta. And then we discretize Newton's method. And what do I mean by discretize? I mean, we use this linear space, right, this tangent space. We use it to do a Galerkin discretization of this bilinear form. Right, this is just the second derivative of E at u theta. This would be our current iterate. This gives us a matrix G. And then we discretize this guy here too, in a Galerkin sense, right? This comes from a dual space. This is like you're forcing in a finite element sense. And this is nothing but the Euclidean gradient of the loss. And then if I then just freely translate from Newton in function space to what I just did with this Galerkin discretization, I arrive at an optimization algorithm in parameter space, which is computable. Here I introduced also a step size. Here this is sort of the analogon of the Hessian matrix in this guy. Dagger denotes a pseudo-inverse because I do not know whether these guys are linearly dependent or not. Here's the Euclidean gradient. So to make that explicit, tying back to the example we had before, this was our energy. And then this matrix G looks like this, right? We have the form with the Laplacians coming from this term here, and we have the boundary conditions coming from here. And now it's time to implement and see how it does. And it performs very well. So this, what I've just shown you is the green line here. The problem is again a Poisson problem to be consistent with the explanation before. And the formulation, right, was the pin formulation. And maybe if you've played around with physics-informed neural networks, it's sometimes quite hard to optimize them. It's certainly very hard to get acceptable or very high accuracies. And here we see a relative L2 error, and of course on a test set of points, not on the ones we've trained on, going down to 10⁻⁷. Sometimes we see 10⁻⁸. And no other method that we've tested can come close. So why do I call that energy natural gradient descent? That's because when we first discovered this, that you could actually optimize pins quite well. We had a slightly different perspective. We came from a natural gradient perspective, and we thought about the Hessian as a Riemannian metric. And later we realized that you can derive this algorithm from this infinite dimensional viewpoint that I've just shown you. And since this was just one example, we tested it on a bunch of linear equations. Also, we used the first order reformulation, time-dependent ones, and it works really well for all of them. We do some tricks, of course. I mean, we do a stabilization, Levenberg-Marquardt kind of stabilization, and so on. But we can get very good accuracies with small networks already for 3-dimensional PDEs, and the training time is not horrible. It can be seconds to minutes depending on your setup and your GPU. So now to really drive that idea home, that you can start from the infinite dimensional viewpoint, I want to show a different example, which is a nonlinear PDE, a Navier-Stokes equation, where we will choose a different algorithm on function space to begin with. We'll choose Gauss-Newton's algorithm on function space. And so if this is the PDE, and again we use a residual formulation, and for simplicity, we ignore that we should add a divergence penalty and the boundary penalty here. Let's just look at this. Then this is our formulation. And then we can ask, okay, how should we optimize that objective function in function space? Then you see it is non-linear inside here, so it loses the convexity in function space because of this non-linearity, but it certainly is a non-linear least squares problem. And if you want to solve non-linear least squares problem, a good choice is Gauss-Newton's method or Levenberg-Marquardt's method. And we do that in function space. So it looks like this. You have the linearization of the residual, after it the adjoint, and that's what you want to invert. And this is just for completeness, the formula, how this form sort of looks like. And you choose an ansatz, u theta p psi for velocity and pressure. The ansatz is again same notation as before. The tangent space is again the linearization. And then you discretize Gauss-Newton's algorithm, again using a Galerkin ansatz. So you get back a matrix G, and this is your Euclidean gradient. And this is how you get the entries of the matrix. So you insert your basis vectors from your Galerkin space that you chose in the form. And again, you're left with an optimization algorithm, which now in this line looks exactly as before. But of course, this matrix G comes from a different infinite dimensional optimization algorithm. And again, this works better than any other optimizer we could find, and then we tried. This is an unsteady 3D Beltrami flow. We could get accuracy close to single precision. We couldn't get 10 to the minus 10 as before, but it's still better by a margin than everything else. So to sort of come to a conclusion here is that you can use this principle that I've showed you, and you can start with different function space algorithms and translate them. And as a matter of fact, they often relate to a known optimization method in parameter space. I haven't shown you this before, but when I introduced Newton, and if you do the computations, you can find out what you're actually doing in parameter space is a generalized Gauss-Newton method. Or if you're solving a saddle point problem, this is the Lagrange-Newton method. So you have a constraint optimization problem. You use Lagrange formalism. You take the gradient of the Lagrangian, use Newton's method to find the zeros of that gradient. That's what I mean with Lagrange-Newton. And if you discretize that in the way I've just shown you, you end up in certain situations with competitive gradient descent, which is proposed was proposed in a totally different community. And Gauss-Newton in function space translates to Gauss-Newton. So I think there's a lot to discover still.
And Marius,
yes?
there's a clarification question. I think it's in slide 16. Robert is asking, is that G or inverse G in the update? Oh, not 16 or 15. When
15. Here, that the dagger is the pseudo-inverse.
Yeah.
So you need to invert the matrix. Yes.
Is it clear, Robert? Okay, cool.
Yeah, I'll talk more about this matrix and how costly that inversion is later on, because I suppose that's a very good question to have.
Okay.
Because of course there is some price that we pay, but I'll talk about that soon.
Cool.
So I want to, because in the beginning I promised that the methods that we derive will provably mimic function space dynamics. So that's what we're setting out to prove now, or just to look at when this is valid. So all the methods that I've shown you before are of this form, right? This guy is now, we said, right, we add a direction. This is this direction, and I assume a certain structure for this direction. It's of a Chez derivative, and then you take it back to primal space with the linear map, with the inverse of a linear map. That might depend on your iterate. So I assume this guy T is linear, continuous, and bijective. Everything we've seen before falls into this setting. We also assume that this map T is coercive. And if we assume that, so the technicalities of what we assumed for T are not so critical, but if we assume that, then we can prove the following, which I call the projection theorem. And let me walk you through this slide. So here is just a repetition of, to clarify the notation of our generic optimization algorithm. And if within parameter space we follow this algorithm, right, if we step theta 1, theta 2, theta 3, and so on, then we can ask ourselves, what is happening on the function space level? What do the functions do, and how do they relate to stepping with the direction dk? And you can see here that actually we are stepping exactly as the infinite dimensional algorithm. This is the dk, but there is this pi guy with this, which is a projection, and this is a Galerkin projection on the tangent space. And then there is an error which corresponds to the step size and the length of the step. So actually, this is what I mean when I refer to provable that we follow the function space dynamics. And let me give you a visualization of that theory. Right? Let's just look at the first 4 images. This is again Poisson's equation. Simple solution. You essentially see the solution here because u theta this is at initialization, so this network is almost 0. So this direction here is really the perfect update direction. If you add this guy onto your current iterate, you'll be at ground truth immediately. So all the other update directions, you want to match that picture. And this is Newton in function space, matches perfectly. Whereas Newton in parameter space, which is a different algorithm, is clueless and gradient descent too. And the same is repeated here below. This is a Courvoisier flow example, so a Navier-Stokes equation, where theta is now somewhere somewhat close to the solution, say on the order of a few % of relative L2 error. So again, this is the perfect update direction. And if you look what Gauss-Newton in function space or Newton in function space tell you, and what they propose to step or what they choose to step, and it matches almost perfectly in the eyeball norm whereas Newton and parameter space or gradient descent are not promising or not good. That we also see that in the optimization. So with that, let's get to scalability, because so far I've just shown you what works well, and these algorithms work so well, you get so high accuracy, but of course there is a price. And the price is that we need to invert a matrix in every step. And to go back to the energy natural gradient, the Newton and function space algorithm, the matrix you need to invert, to assemble, of course, and to invert is the following one. And this guy here. But if your ansatz is non-local, then this matrix is dense. It is typically rank deficient and ill-conditioned. So you have a pretty challenging matrix to deal with. Small scale, small networks are fine. You can do an SVD, maybe because this matrix is positive semi-definite, you regularize it a little bit with a Tikhonov regularization, you add an identity, you could use a Cholesky solve, you'll be fine. But as soon as you scale up the size of the networks, this is really challenging. So what are our options to scale it up? You can use a matrix-free formulation that works. This system needs to be solved. You need access to matrix vector products. You can get them. The details are, for example, in this paper. How to get the matrix vector products, you just rely on that you can reformulate it in parameter space as a Gauss-Newton matrix, and then you can do that. You can use CG, but CG iterates for a long time because the matrix is ill-conditioned. But at least you can scale up. A different strategy is to derive cheap to invert approximations. And this is where I'm going to focus on the rest of the talks. If you take derivatives of linear network layers, then you can find Kronecker structure in that matrix. And this Kronecker structure can be leveraged to build an approximation of G. And of course, you can also aim to combine these two strategies. You can build a cheap to invert approximation, use it as a preconditioner in your CG. So let's get into the Kronecker-factor approximation. So very roughly, what we want to do is we have that matrix G. You think of your ansatz as a neural networks with layers. This is what this 1 to capital L corresponds to, and you discard cross interaction between layers. Then you're left here with capital L many matrices, which are still quite big, and then you aim to approximate them as Kronecker products of two smaller matrices. You approximate them as Kronecker factors, of course, because you can change the inverse with the factors, and this really gives you a dramatic speed up in the solving. So if you say my linear map, my linear layer and my network maps from Rn to Rm, we're ignoring biases here, then this matrix, then the block matrix up here is of size n times m squared, but the Kronecker factors are just n times n and m times m. So you have a drastic speed up, and you can scale up by a large margin. So how do you get that Kronecker structure? I'll show you that with an example where the Laplacian terms, so which is again motivated from the Poisson, is coming from the Poisson equation. So what you can show is that the matrix G, or the layer, that the block matrix corresponding to a layer, is of that form. So this is the Jacobian with respect to the Lth weight matrix of this expression, transpose times itself. And where you can find Kronecker structure is if you take derivatives of this map, theta now is a weight matrix, and you map the weight matrix to weight matrix times a fixed vector. And if you take the Jacobian with respect to this matrix theta, then you'll get Kronecker structure. Now, if you think about chain rule, what we need to do to get out this this Kronecker structure of in our complicated computation graph is we need to know what the children in the computational graph of this map is. So the L weight matrix mapped to Laplacian of u theta at a data point. And I'm not going to go into the details, but what how we could disentangle the structure is that we relied on forward mode, or also called Taylor mode autodiff, which is also what was recently proposed in the forward Laplacian paper, which is from the VMC community. So let's just look at this graph. Think of a multi-layer perceptron. Theta are your trainable weights. Just ignore biases. This is a weight matrix, and we have L many. This is your input. So going through here just gives you your neural net prediction. And of course, the weight matrix enters as a matrix product to this vector. But of course, we do not only want to compute the output of the neural network, but we also want to compute first-order derivatives and second-order derivatives, possibly more, but let's focus on them. So forward mode, as in contrast to back propagation, you just push everything forward, right? You multiply the matrices from the other end. So this is what's happening here. And when you write out the recursion, you see that the weight matrix doesn't only enter into in the forward propagation as a matrix product, but it does also enter in the first derivatives, so in the gradient, and also in the Laplacian. So then if you factor this whole thing exactly as the colors indicate with pink and blue, then you can leverage the Kronecker structure. And I really do not want to go into detail here, but this viewpoint lets us compute exactly how that matrix looks. It looks horrible, 3 sums, a lot of symbols, Kronecker structure here. So note, this is not an approximation, this really is an equality. And then the KFAC approximation, which is hand waving, admittedly, but is put into great use in the deep learning community, is to swap the sum and the Kronecker. And we also here drop indices that are different from each other. So we really end up with an approximation as exactly as I promised to you. So the matrix G can be approximated as A Kronecker B. So this was the outline. It's technical. You can find the details in our recent paper, which is going to be in NeurIPS. And I've showed it to you for the Poisson problem, but it does actually work for general nonlinear PDEs with the pin formulation. You could do it for very rational formulations, the DeBriggs method. We haven't looked into neural operators. This requires more work. So there we're uncertain how it would play out. And typically, once you have this approximation for G, there's a whole bunch of bells and whistles you put on top of your optimizer. It would be a trust region method for step size choice. You would do exponential moving averages for the KFAC matrices. You would maybe update them infrequently. So there are many things you can do. And as said, you find the details. It's not a preprint at this point anymore in this paper here. And then I want to show you some experiments just to illustrate that we keep the good performance or we can reproduce the good performance in the small experiments, but we can scale to big networks. So to warm up, here's again the Poisson equation. The blue lines are the methods that do not scale, right? That require a dense matrix that you need to invert. The black lines are KFAC. The light green line is the CG version of the natural gradient. And then we have first order methods in red and orange, and the LBFGS in dark green. And what you see here in the small example, this is always relative L2 error over time. The naive way of doing things is actually the best one. Whereas as soon as you scale up, this is the dimension, these are the number of trainable weights in your neural network, then at some point you cannot do the naive approach anymore, but the black lines always are among the best performing. So now we move up in dimension. We do a heat equation in 4 spatial and 1 time dimension, and the picture is similar. And finally, we went up to 1 million parameters with a 100D Poisson equation. Actually, I believe this experiment is still running here. We did a Bayesian insert for the hyperparameters. So there's a lot of work that goes on into these numerical experiments and to really fine tune these optimizers before then, after finding good hyperparameters, they're really ready to use. So this is by no means the end of the sort of journey for really making the best out of this optimizer. And then just to put it in context, or put this KFAC in context, this approximation allows us to scale to millions of parameters. That works really well. I still call them preliminary, somewhat preliminary numerical experiments. They compare favorably to all established optimizers, often outperforming them. And you can do the approximation I've showed you virtually to any PDE. But it will be interesting to see more equation. We're working on that right now. And of course, maybe this is the main point, the KFAC approximation is not so easy to set up. So you need a dedication to implement that and to make it run. And with that, I just want to wrap up and maybe give an outlook, I think, of what can be done next in sort of that area, and where I think future work is, future efforts are well placed. So I think the function space viewpoint is far from exploited. I think there's still many things one can do. There's many concepts you can still translate, among them, for example, trust reaching methods, infinite dimensional ones, or operator preconditioning approaches. I'm also not aware of any convergence theory that really properly separates the function space and the parameter space. And I think there's still a lot to do on the KFAC side, on just improving the optimizer we've built. We haven't really tried to use it as a preconditioner in matrix-free implementations. Currently working on a high-dimensional PDEs like Fokker-Planck, Hamiltonian, Jacobi-Bellman equations, Schrödinger equations. I think there is a lot to come. And with that, I want to thank you for your attention and happy to take questions.
Awesome. Thank you so much for the wonderful talk. Very nice, very nice. So let's have a, yeah.
Yeah, may I maybe exit full screen mode so that I see you if somebody is asking questions? Or maybe that's not a good idea. I leave it open so that we can go back to slides for the questions.
Yeah, the people can unmute themselves and then ask questions directly. And yes, let's have a Q&A sessions. I can start, I guess. For more general nonlinear problems, you switch from the Newton to Gauss-Newton. Is it because, to avoid, the computing the full Hessian informations, because that somewhat
I can tell you why we do that. So when the objective is non-convex, of course, you have no guarantee that your Newton matrix is definite, right? It could be indefinite.
Mm-hmm.
And then you have no guarantee that what you step is actually a descent direction.
Mm-hmm.
Only if you get close to the minimizer,
Mm-hmm.
then you know that Newton's matrix will get definite.
Mm-hmm.
And when we do the numerical experiments, we observe precisely that if we use Newton in function space, right, and discretize it that way, and step, then it's not stable. It doesn't go in the right direction. But if we're close to the minimum and use Newton, then it is very close to Gauss-Newton in function space, which is also to be expected. And we found Gauss-Newton just to be the more robust choice, because you linearize, you always have the guarantee that you're taking a descent direction.
Cool. Very nice. Not just for, avoiding the implementation cumbersome, but it does actually
Yeah,
works
I
better.
mean, because you compute the Newton matrix, right? The infinite dimensional object is always something that you compute with pen and paper. So
it's not a big
there
deal.
is maybe a little bit, it's maybe a little bit more difficult to compute with on pen and paper the Newton matrix than to compute the Gauss-Newton matrix, but it's comparable, and the implementation is maybe an epsilon more difficult for the Newton matrix, but you can do both. But the performance of the Gauss-Newton is just more stable.
Okay, wonderful. All right, Stephanie, do you want to unmute yourself and ask a question?
Yeah, thanks for the talk. I was wondering if you can comment more on the connection to the natural gradient and Riemann manifold. You mentioned that's the angle you came from at the beginning. Did you divert from that, or is it still the same?
So many of the methods I've shown you, maybe I go back to a slide where I can easily explain that, can be interpreted as, maybe that's actually a good slide. Yeah, that's a good slide. So many of the methods can be interpreted as a natural gradient method, and they can be interpreted as a natural gradient method precisely when this T-map here, right, this guy is symmetric, right? If this object really here is an inner product on function space, then actually you're doing a natural gradient method, or a Riemannian, right? A Riemannian gradient descent method. But there is no need for T to be symmetric. If you look at saddle point problems, and there was this example of Lagrange-Newton and competitive gradient descent, then this T is not right. And then the method you get is not a natural gradient method, is not the Riemannian metric that you're using to design sort of your precondition for your gradient. So we switched to function space viewpoint because it's more general. But everything with the natural gradient descent is still valid, is still a good viewpoint. Does that answer your question?
Yes, it does. I might have some follow-up questions later on. I think I want to digest that a little bit, but I might shoot you an email if that's okay.
Yeah. I'm happy to take emails, of course.
Awesome. Great. Any other questions? While someone has a question, I have another question. So if you go to slide 22,
yes,
the size of the matrix is proportional to the size of the ansatz, right?
Yes, exactly.
And
the dimensionality of your parameter space.
And I'm guessing that's the performance of this gradient descent will depend on the size of the ansatz as well. I mean, more the better, I guess.
Say that one more time. What will depend on the ansatz as well?
The performance, like the convergence behavior of this.
Oh yeah. So I mean, if your ansatz is more expressive than sort of you expect, right? It's richer. You can do better.
Yeah,
it will always depend on your specific problem, right?
So
sometimes you need a bigger ansatz. Sometimes a smaller is sufficient.
Oh, okay. So I see the the balancing game here.
Mm.
So you need more ansatz, but if you increase the ansatz, then your matrix becomes bigger and bigger, and you're dealing with a dense matrix. So it's harder to solve numerically, and so there must be some sweet spot between those two balancing game. If you can comment on that from your experience.
Yeah, so I can say something. I don't know if this will be a perfect answer, but if you're looking into, simpler problems, where maybe your solution is not highly oscillatory, but it's okay, somewhat smooth, not too complicated, then we found that you can actually use relatively small networks. Like the default would probably, right, you set something up in Jax or PyTorch, and you just go big because the frameworks will do it and your GPU can do it. But often it might not even be needed, and then it's of course easier to get it to run if you reduce the size a bit. And these algorithms play nicely with that. With Adam, sometimes, or with stochastic first order methods, sometimes you have the feeling you need to go big to make it work okay. But these also work quite well in a smaller network and in a smaller regime. But of course, if your function is complicated, if you're solving a many electron Schrödinger equation, there is no way you can use a small network. And I think then there is no way around using some approximation of these methods. I mean, as a matter of fact, this KFAC is, I think, the gold standard for neural network-based many electron Schrödinger equations. In this community, they do not use PDE operators in the preconditioner. They use sort of an L2-based version of that, but they found this to be crucial to optimize wave functions.
Okay. My next question is about the Kronecker, K factor, you call it.
KFAC, yes. Yeah.
Yeah, that's a approximate of the Jacobian, the way of computing.
So yeah, exactly. So there's two approximations that we're doing. There's this matrix G. We do a plug diagonal approximation of that matrix. And then the diagonal blocks, you approximate them as Kronecker products. So it's a very aggressive approximation of G. Yes.
Okay. And I'm wondering if it can be, since it is approximate, it can be used as a preconditioner.
I think it can, and it's relatively high on our to-do list to actually try that.
Oh, okay. Oh,
yeah.
Any other question from audience? You can unmute yourself and then ask questions. Well, if not, let's thank our speaker today. Thank you so much. It's in Europe right now. What time is it there? It's pretty late.
10 to 7.
Oh, 10 to 7. Oh, okay, not that bad. Hope you.
No, not bad at all.
But I happens to know that Marius has 2 kids and very young, 4 years old and 6 months, and
they need to go to bed now. Yes, and they'll require my help.
They require your help.
But thank you so much for having me in this wonderful seminar. Thank you so much.
Yeah. Well, my last question would be before we log off here. Obviously, the national lab, they deal with a very, very large scale problems, and also the complexity is multiphysics and multi-fidelity. That's sort of the problem. So, it's still questionable. Your method is how it is applicable directly to those complex problems. I'm sure there's a way to go. I mean, more research and more development is required. So I will do my best of how we can collaborate or bring this idea to the multiphysics and
Yes, if you are interested, if you have a high, I think these neural network based methods for PDEs are especially interesting for high dimensional PDEs, or maybe potentially high dimensional parameter spaces if it's a parametric PDE. If you have a realistic problem, yeah, feel free to reach out. We're currently working on an easy to use PyTorch implementation of the KFAC method that I've shown you. So please let me know if you're interested in trying something out. Please reach out.
Okay, well, we'll do. Well, thank you so much for the wonderful talk, Marius, and let's applause to our great speaker today. And that was very nice, and we learned a lot from you, Marius. So we appreciate it.
Thank you so much. Bye.
Thank you. Bye.